All right, so questions? Yeah.
Can you go over try and test?
Try catch, sure. Absolutely. All right, let's just play with some code. All right, so here's some code that throws an exception, doing a division by 0. So we don't know if this is going to throw an exception, so we're going to put this inside a try block. So let's put some prints in here. Let's say we're inside our try block. Down here we'll say we're inside our catch block. Alright, so we'll always be inside our try block. If we do this operation and it fails, we should jump to our catch block with an exception. So we were in the try block, we tried to do this division, then we jumped into the catch block and we got an exception, which was arithmetic exception, division by 0. If j was 1, right, we're in the try block, we never go into the catch block. And let's just print a message when we're done with the whole try-catch experiment. Right, so if we don't get an exception, we're in the try block, we don't do the catch, and we end up outside. If we do get an exception, we're in the try block, we jump into the catch block, do whatever it says in there, and then we go to the outside try block.
So basically it's like a true-false statement.
Basically a true-false. It's saying try to do the following statements, and if everything succeeds, skip the catch part, the else part. But if anything fails, we'll jump down and we'll do the catch part.
The quiz talks about a finally statement.
Yeah. So we're going to have a finally part which says in the finally part. So if we get an exception, we're in the try block, we throw an exception, jump into the catch block, and then we go into the finally block. And then we're done with the whole try catch finally thing. If we don't get an exception, We start off in the try, we skip the catch, we do the finally part, and then we're outside.
So if we assign the not integer instead the double, because double can handle the infinity case, so it's gonna be try.
Yeah, if they're doubles, we won't get an exception.
Uh,
Right, but integers we will.
What's the point of the finally if they're always?
Yeah, what's the point of the finally as opposed to just the outside try-catch block? Because there's something really quirky in here. So typically, when you get an exception, that's a good place to return, right? Because maybe the exception says we can't do anything more here. So if we do this division, i's got a new value. Otherwise, we're going to say we got an error message and we're going to return. And let's set j equal to 0 so we do get an exception. Okay, so check this out. We did the try, we jumped into the catch block because we got an exception, but we still did the finally part before we returned. So try to execute this. Jump down to here. But then before the return gets executed, it comes down and does the finally block. I hate that personally. That seems really weird to me, but it's a thing. I don't hate it, but I've never used it.
So it's just something that will execute before return is called?
Yeah.
Does that happen regardless of where return is called?
It's only if you're returning in the catch block,
Okay.
right? At the point where you're about to return, if you're returning from a catch and there's a finally block, it'll jump down and do the finally block first.
Okay.
I don't know what happens if you return from the finally.
So the only, so try and finally only work together then?
Try and finally work together, and catch and finally work together.
Okay.
And I think, let's see if it happens here. So suppose we don't get an exception and we just do our try block and our try block says return. I think it will still do the finally block. Yeah, so even if you don't get an exception, if you're going to return from your try block or your catch block, it'll come down to the finally block first. And it's smart. When I had my code like this, it wouldn't compile because it realizes there's no way I'm ever going to execute this outside try-catch block statement. Because if I succeed, I'll return. If I fail, I'll return. And so it was giving me a compile error saying you got unreachable code. It's a feature. Does that help? Okay. I should get a network connection. Alright, there's another example on the website. I got tired of constantly typing class main, public static void main, string bracket args, curly brackets all over the place, so nothing fancy here, but I made a command I call init. I can say init haha, and it makes a file called haha.java, which says class haha, public static void main, etc., etc. So I can save like 30 seconds every time that I start a program in here. So init is a file called doinit. which has a fair amount of code in it, but it's just bash code. If I just say init, it sets the file name to main.java, so I don't have to say init main.java because that's the most popular class name I use. If I say init haha, it will detect that there's no .java and it'll stick a .java on the end. So I can just say init in the name of a class, and if the file that I'm trying to create already exists, it will, you know, use a -e to see that it exists, and it will refuse to create it and exit. Otherwise, I check to see if the file is main.java, and if it is, I just copy a template into that file. Otherwise, I pull the class name out of the file name by taking everything up to .java, and then I cat my template, but I change uppercase main to whatever my class name is and put that into my output. So this is why we live in Linux, right, and Unix, because we can do stuff like this. This was, you know, something I did while I was having breakfast yesterday and was getting ready to type class main again for the millionth time, and I was like, no, I'm done with that. So, you know, it takes a few minutes to put together, you dust off your bash programming skills, and there's tons of stuff you can do like this. And it makes your life a little more efficient, a little more pleasant, it's fun, right? And if you're working on some big project that's going to take you 2 weeks to do, and you can sit down for 10 minutes and get something that works, that's like a nice little dopamine hit. It feels fun, right? I did something and it works and I can use it now. That's always good stuff. And it keeps your shell scripting up to date. And the next time you want to do something, maybe you've got a template you can start with and modify from there. And there's tons of stuff you can do with this, right? So I have this doc command that that I use to pull up Java documentation. And this took a little longer than 10 minutes to write. I kept modifying it though along the way. But I can say doc, and it shows me the index for the Java documentation. So if I just do doc, it brings up this general index page. Or I can say doc, and I can put in a keyword, right, $1. And if it has any slashes in it, it assumes I'm looking for a web page, right? And it will go into the directory where I have all of the Java documentation. And it will run something called docfind, which is another little script that basically looks for any file that has that that URL in it. And if it finds a series of pages that match that, so how do you find that? You just do an ls on that documentation directory, right? Find all the files, do a grep to search for whatever keyword you're looking for, like if you say jpanel, just list all the files in the documentation tree, look for a jpanel, ignore a case, and you get back a bunch of file references. And then all of this stuff is looking for the shortest file reference, because usually that's the one that I'm interested in. So java.io.file or java.io.supplemental stuff.file, right? I want the short one. And so this just does stuff in bash, takes this space separated list of file names, turns it into an array, loops through them, finds the length of each entry, and remembers what the shortest one is. So this is like a 224 exam question, right? And then runs that through Firefox to display that particular page. If you give a particular page that has slashes, it uses that page and brings it up, and so on and so forth, right? It's not something I'm going to sell or publish or anybody else is ever going to care about, but, you know, it makes it quick for me to do things like, let's look at what a jpanel is, and there it is. Or I can say doc all, and it'll show me all the pages of information that are available. So there's one under swing class use, and there's one just under swing. So I want to keep encouraging you as you're working in this course, but also as you're working in other courses when you go on to a university and so on, right? Keep in mind that you can usually tailor your environment to your liking, and keep some part of your brain alert to the possibility of something you can do that's going to make you more efficient or happier or more comfortable or something, right? And everybody seems to develop their own toolbox along the way, and sometimes it's stuff that you've taken from Unix, sometimes it's stuff that somebody did that you've got a copy of, sometimes it's stuff that you just wrote on your own, or a mixture of those. And all this stuff is usually available in source code, so you can take it and tweak it, or draw inspiration from it and come up with your own, and so on and so forth. And that's a lot of how Unix got to be Unix, right? A lot of the stuff was just things that people found useful and they caught on, and somebody started supporting them. All right, let's play with linked lists some more. So I've made a rectangle class. It's got a height and a width. It's got a constructor that takes height and width, and it's got a toString method. So let's make a linked list of rectangles. Linkies list. All right, that's all I need to initialize an empty linked list of rectangles. Rectangle has to be in the current directory as a class, and this should make a list 1, which is our linked list. So let's add some things to our rectangle. And I'm just going to make some squares. And I'm going to put them in a very uninspired order so that if we look at the 5th rectangle, it's a 5 by 5, just so we can see what we've got. And I'll avoid my syntax error. And then let's print it out by just concatenating it to a string. You ready for this? Bingo. There's our linked list of rectangles. And I think that's pretty darn cool. Right? The linked list is coming out with this comma-separated list of elements, and those elements are being printed using the toString method of the element. And since I had a toString and rectangle which said print the height and x and the width, I got this nice display of the elements in my linked list. So that's pretty sweet. Let's make a second list. Alright, so I'm going to make a list 2. I'm not going to construct it. It's just going to be a linked list of rectangles. But I'm not going to make a constructor. I'm not going to call a constructor for it. And it's not even going to compile it. So if it compiled it and it ran it, I would get a null pointer exception when I tried to call the toString method on list 2. But the compiler can actually tell that list 2 has not been initialized. So let's copy list 1 to list 2. So we're going to set list 2 equal to list 1. Let's print out our lists. And this is not surprising. List 2 is a copy of list 1. All right, so linked list, what can we do? We can remove an element from a list. So let's try that. So let's remove the second element of list 1. Second element's actually going to be index 1. So I'll remove that from list 1, and let's take a look at our lists after we do that. And what happened, we removed the second element from list 1. We, in the process, removed the second element from list 2. Does that make sense that that's what should have happened? It depends how we think of these lists. So when we say list 2 equals list 1, right, list 2, think of it as a pointer to a list. Okay, it's a pointer to an object. When we say list 2 equals list 1, we're setting list 2 to be the same pointer. In other words, it's pointing to the same object. So here's a linked list. List 1 we can think of, even though we don't do pointers in Java, we can think of list 1 as a pointer to that. When we say list 2 equals list 1, we're basically saying list 2 is also pointing to that. If we were in C, and this was a struct linked list star, this would be a memory address, the location where that list begins in memory. It's a big integer. If we say list 2 equals list 1, and this is a big integer, list 2 is equal to the same big integer. But when we say what's list 2 pointing to, hey, it's the same thing list 1 was pointing to. This is why if we had two linked lists that looked exactly the same and we said is list 1 equal to list 2 equal, right? Unless they're pointing to the same actual list, they're going to say, no, that's not equal. Right? This is why strings that have the same letters don't pass the equal test even though they have the same letters, because they're not the same location in memory.
Does the same thing happen if we had initialized list 2 and new list 1?
Yeah, so if we do this, right, now list 2 has its own essence, but that list that we constructed gets thrown away basically when we say list 2 equals list 1. And this is the thing where you have a pointer to a struct node, but you say, you know, struct node star this equals malloc, and then the next statement you say variable equals, you know, temp or something. The thing that you malloc is not being used anymore. So when we do this, list 2 is totally separate from list, but when we do the assignment, then list 2 is pointing to the same thing as list. Yeah.
How would we use this built-in linked list if we wanted to keep them in a particular sorted order, like say largest width first?
That's a good question.
Because I didn't see every single one of them, but I didn't see one that looked like it put it in a sorted spot.
Yeah, I think the barehanded way to do it would be just make a loop, right? And go through and get each element one by one and compare it using whatever method you're using to compare. And when you get to a spot where the thing that you pulled from the list is bigger, then can we insert in between?
It would be nice if there was like an add that took a Boolean statement.
Yeah.
It would add it when that Boolean became true.
So let's see what add does. Let's add a rectangle to position 3. So this is index and element. So and I'm curious if it's going to replace that element or actually insert it. So it looks like it actually inserts it. It shows everything else down. So if you want to insert something in sorted order, right, use a get loop, pull off each element. When you find index I is bigger, go ahead and insert it I.
So if I wanted to write my own method that just took add, a number and then a Boolean, and it added it when it went down the list and added it when that Boolean became true.
Mm-hmm.
What was I think we went over it, how you could make a class that was basically linked list but with my own methods.
Yeah, so you could extend this unless it's final. And it doesn't look like it's final. So you could make, my linked list extends linked list.
Extends.
And you could add a new method to it if you wanted. Yeah.
So is saying list 2 equal list 1 similar to cloning list 1?
No, so that's where we're going next. So at this point, list 2 and list 1 are the same thing, right? So now let's do something different. So let's set list 2 equal to list 1 dot clone. And if you try to compile this, you'll get an error saying clone returns an object and you're trying to assign it to a linked list of rectangles. Right? Because clone doesn't know what kind of thing you have, so it's just defined to return an object. So we have to convert it from an object to a linked list of rectangles, and we can do that by casting. So parentheses, list the type of thing that you want to cast to. And now the thing on the right is a linked list of rectangles. That should get assigned to the thing on the left. And I'll get a lint warning when I do this, and I haven't had a chance to dig into how to get rid of that. But this will work. So now let's repeat our experiment. So after we've cloned, let's remove the second element of list 1 and see what happens. Alright, so here we remove that 3 by 3 from list 1, but list 2 still has the 3 by 3 in it. So after we've cloned, now we've got a completely new linked list, which initially looks just like that old list, but that's what list 2 is pointing to. And so if I remove this element, I haven't changed list 2. Yeah.
So is that the best way to copy a list and then manipulate only one of them?
If you want a copy of the list and you want to manipulate only one of them, clone can be a good way to do it, but it's not always enough. So we're going to make this even weirder now. So let's change the last rectangle in list 2. So, what can we do here? We can say get. Get last. Let's do get last. So list 2.getLast should be the last rectangle in list 2, which is a 6 by 6. Let's set the height to 99. And the width to 99. So in list 2 we're going to change that last rectangle to be 99 by 99. And then we'll go ahead and we'll print out our lists. And it did what we asked, but it also changed the last rectangle in list 1. So even though we used clone and we got a separate list and we can delete things from one list without deleting them from the other, they're not totally independent lists. The things inside the lists are identical.
So why did it change list 1 if list 2 is equal to list 2?
Because here's kind of what the picture looks like. Here's list 1. It's got a bunch of nodes pointing to nodes pointing to nodes. Here's list 2. It's got its own nodes pointing to its own nodes. Well, these nodes have a data field inside, right? So the data field in here is basically, you know, a 1 by 1 rectangle. And the data field in here is a 2 by 2 rectangle, and the data field in here is maybe a 4 by 4 rectangle. The data field in here is the same 1 by 1 rectangle and the same 2 by 2 rectangle, and then maybe its own 3 by 3 rectangle. Right? So if I change this thing's rectangle's height and I check the height of this thing's rectangle, I've changed it. So when you look at clone, it says returns a shallow copy of this linked list. Okay, so this is the idea of a shallow copy versus a deep copy. A shallow copy is just saying build a new list, right, comprised of the same objects that we had in the old list. So we can change the pointer, you know, the thing that this node is pointing to, so that it points to a 3 by 3 instead of pointing to a 4 by 4. Right, we can change where this points independently, but the things that it's pointing to, those are basically still shared between the two lists. So if we really wanted to separate this, if we wanted our own 1 by 1, 2 by 2, 4 by 4 rectangle up here, you have to do a deep copy. And a lot of times you have to do that by hand. So you could make a loop, you could read this thing, find its height and its width, make a construction out of those, and store that in this element of the list. That's a perfect hand signal when I need to switch, by the way. That's worked a few times now.
What was it?
I don't know, but it somehow works. It's like enough motion to catch my eye, and then... All right, so that's the deal with the clone. That's the deal with making copies. So you got different levels. You can just do list 2 equals list 1. That's pointing to exactly the same object. You can do a clone, which gives you something that's independent in some ways, but the thing it's made up of are still the same objects. Or you can write code to do a deep copy. And then you've got two totally separate lists that are completely independent of each other.
If you change element 2 in the copy, it will only change the corresponding one in list 1 regardless of which element it is?
Yeah.
Okay.
Yeah, because it's and did we do that? Yeah, because it was the fourth element in list
Yeah,
1,
and
fifth in
then
list
fifth.
2, but they're pointing to a rectangle, right? And they're both pointing to the same rectangle. Yeah, it's an interesting note.
And so will the same thing happen if you like add this thing?
So I can add something to list 2, and if I add a new rectangle, right, then it would be an independent entity. But let's try this. Let's make it really twisted. So let's see what methods we have. So we can add to the end of the list. So let's do list1 dot add list1 dot get first. So let's get the first element and add it to the end. Alright, so now we got a 1 by 1 on the end of list 1, not on the end of list 2. Okay, because we're manipulating the list, that's fine. And let's change the dimensions of that first rectangle. Alright, so we'll get the first element, we'll set the height and the width to 42. And there again, we changed the first element, but that ended up changing the last element. Right? Why? Because we said take the first element and add that to the end of the list. And we literally, maybe not literally, because they don't do this in literature, but we, put another node here and we said point to that thing, that's the data value. So this gets into all kinds of weird levels related to call by value, call by reference, and it's probably best not to think too deeply around it unless you want to just kind of sit in the grass and look at the sky and ponder for a while. When you find yourself making large data structures and you need copies of them, that's when you definitely need to worry about this, right? And usually a deep copy is going to be safe because you don't usually want multiple things intertwined like this. Sometimes you might though. So you just want to be aware that there is an issue here, right? There's different levels of copying, and which one is the right one, it depends on what you're doing and how your structures are set up. And honestly, the first few times you bump into this, it's kind of confusing, right? You end up drawing pictures and doing experiments like this and scratching your head and talking to people and finding a way to make it work, and it sinks in more over time. Not going to come up for us in this course, right? Because we're just not working with those kinds of scenarios. But it's something to keep in the back of your brains. We got 3 minutes. We're gonna do Open Lab tomorrow. Tomorrow's Thursday, right?
Yep.
All right, I'm not jumping the gun this week. So Open Lab tomorrow, if you want to work on Eclipse or PA3 or go over PA2 or anything like that. Friday, we'll start looking at HashMap. So HashMap is an implementation of a hash, the way we talked about hashes in 222. So if you want to dust off your notes on hashes, right, it's basically an associative array. There's a key-value pair. You can store data associated with a key. You can retrieve data by using a key. We can search for data. We can delete data, and so on and so forth. And all the details of, doing modulo 11 and adding ASCII codes, we're going to ignore all of that. That's all handled inside this class for us. And our interface to this is basically things like clear out everything in the hash, tell me if the particular key is contained in the hash, get the thing associated with a key, put a value associated to this key, and so on and so forth. So basically initialize, which is a constructor, just hash map, fetch, retrieve, store, delete, clear. But this is also going to get us to where we can talk about iterators. If we want to see everything that's in the hash, we're going to create what's called an iterator, and we'll talk about that on Friday also.
I have classes that are just called V.
So V is part of a generic because we can use any kind of object we want for the key and the data. So when we construct this, we're going to specify both the type of the key and the type of the values. So those will get filled in.
So if you see classes that are like one line like that, is that just an indication?
Yeah, check the top, see what it says for up here. You should see them listed in angle brackets. All right, I'll see you tomorrow.